Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. In my last video on sodium-ion batteries, I received pushback from fans of the chemistry, suggesting the forecasts I shared weren't bullish enough, and therefore biased. In response, I'd say that all forecasts are wrong, it's just a matter of how wrong, so I don't expect to nail it. However, with respect to bias, if anything, my bias was actually in favor of sodium-ion. That's because I covered the chemistry on a component-by-component basis and left out the technical challenges involved in manufacturing those components. Why? Because I don't view those technical challenges as showstoppers, and so it would have been a distraction to get into the weeds on challenges that I'm confident will eventually be solved. However, that may have given the impression that sodium-ion is already a solved problem, and it's smooth sailing from here. So today, I'm going to get into those technical challenges so that bulls and bears alike can factor them in as part of their own expectations for the growth of the sodium-ion battery industry. And most of the information will come from none other than CATL itself. Before we begin, a special thanks to my Patreon supporters, YouTube members, and Twitter subscribers, as well as Rebellionaire.com. They specialize in helping investors manage concentrated positions. Rebellionaire can help with covered calls, risk management, and creating a money master plan from your financial first principles. Let's dig into this paper by Chong Li et al. Titled Progress and Prospect of Industrialization of Sodium-Ion Battery in China, which I'll also link in the description. Every author in this paper works for CATL, and it was first published in October of 2025. I think that's worth repeating. This paper is less than 6 months old, and every author is employed by the company that most people assume will become the leader in sodium-ion battery manufacturing. To ensure that I haven't misrepresented their work, I contacted Ulderico and he reviewed this script. I've known Ulderico since the early days of this channel, and he has a wealth of knowledge on the bleeding edge of battery development. He's currently in charge of CATL venture capital activities outside of China, where he focuses on discovering and assessing new technologies. Previous to that, he was a research manager for CATL. He's currently a project director at the Volta Foundation, and in the past, he was the battery research lead at Row Motion, which produces some of the best analysis in the world on the battery industry. However, as always, despite the peer review, any errors in this video are due to my own attempts at simplifying complex subject matter. Starting with the cathode, one of the sodium-ion cathode materials that CATL has used in the past is what's called Prussian white, which is considered to be a type of PBA, or Prussian blue analog. The research paper states that the commercialization of Prussian blue analogs is lagging behind that of other sodium-ion cathode types in recent years due to 3 key issues. First, the production method it uses results in water retained in the crystal structure of the cathode, which increases unwanted side reactions that cause rapid performance degradation. Second, Prussian blue analogs use cyanide as one of the components of their crystal structure, creating safety hazards during material preparation and use. So, battery systems that use Prussian blue analogs produce large amounts of highly toxic cyanides at temperatures above 200 degrees Celsius, which hinders their industrialization. Third, pressed density. As I said in the last video, sodium-ion batteries in general have low volumetric energy density. But that's more true with Prussian blue analogs because they have a cubic crystal structure that doesn't compress well when laminated to the current collector. The second class of sodium-ion cathode is layered oxides, which may also be used by CATL that tend to have much higher energy density but are less chemically stable. We don't need to go through all the challenges of layered oxide in detail as well. but they also face issues like alkali residues on the cathode that cause severe gas generation during cycling and storage, poor air stability which requires strict humidity control during manufacturing, and structural instability within the cathode crystal during cycling, particularly at high voltages, which results in degradation and shortened cycle life. The third class of sodium-ion cathodes are polyanionic. These seem to have the fewest manufacturing issues, but, like Prussian blue analogs, typically have some of the lowest volumetric energy density, and are often less capable in terms of charge and discharge speed due to lower conductivity. As a side note, here's a handy reference from the CATL paper comparing the spider plots of each sodium-ion cathode chemistry. FYI, scale-up availability refers to how compatible the chemistries are with current equipment and processes used for lithium-ion. But, as I showed a moment ago, that, of course, doesn't mean there aren't engineering, chemical, and supply chain issues left to solve. Next, the anode. As I said in the last video, while graphite is the preferred anode material for lithium-ion batteries, hard carbon is the preferred anode material for sodium-ion batteries. That's because although sodium ions can intercalate into graphite, it's a tighter fit, and sodium-ion electrolytes are more compatible with hard carbon. Given that graphite and hard carbon are both made of the same element, carbon, that should mean it's easy to swap the graphite for hard carbon, right? Not exactly. First, it's still early days in terms of developing the supply chain for hard carbon. Hard carbon can be derived from fossil fuel byproducts such as pitch, or by pyrolyzing or heating almost any type of biomass. As it's heated, biomass tends to retain some of its original structure. That means the choice of biomass used to make the hard carbon determines characteristics such as its surface chemistry and porosity, and therefore its electrochemical activity. There are workable hard carbon anodes on the market, but they aren't as mature as graphite, which has been optimized for decades. That lower maturity level means lower performance in areas such as first cycle Coulombic efficiency. Low first cycle Coulombic efficiency means the first time a sodium-ion battery is charged and discharged, it can permanently lose a lot of its storage capacity to side reactions. Second, when biomass is used as feedstock for hard carbon, it tends to have large variability due to regional and seasonal factors, which make large-scale production a challenge. Third, although biomass feedstock for hard carbon anodes is generally cheaper than the feedstock for graphite, purifying the feedstock requires an energy-intensive acid-alkali process, which adds cost compared to graphite production. The poor electrochemical activity, inconsistent biomass feedstock, and additional purification costs all add up to a material that's more expensive and more difficult to source than the graphite used in lithium-ion batteries. I could continue on here and cover the challenges involved in every other component and process involved in making sodium-ion batteries, but I feel like it would be beating a dead horse. By covering the two major components, the cathode and anode, you should have a clear understanding of the key takeaway of the research paper, which is that sodium-ion batteries aren't a solved problem. It's still very much an emerging industry. What are the implications of that? First, until some of the technical challenges are solved and the supply chain matures, the production cost of sodium-ion batteries will remain uncompetitive. That means sodium-ion batteries are going to be fighting an uphill battle in terms of cost against LFP batteries, which are lower cost and a superior product for most use cases. Second, LFP batteries will continue to scale more rapidly on an absolute basis because it's easier to ramp a mature supply chain with established processes. Yes, sodium ion will grow more quickly on a relative basis or percentage growth year over year, but it's working off a much smaller base. So in the next few years at least, its impact will likely be supplemental to the battery industry as a whole rather than transformative. That's not to say it won't be transformative at all, because for some niche applications where fast charging or cold weather performance are a priority, it will be. But for most use cases, LFP will remain the dominant technology simply because it's more widely available. Third, the resources of the sodium-ion battery industry are stretched thinner because unlike the LFP battery industry, which is all focused on the same basic cathode and anode, the sodium-ion battery industry is pursuing several different cathodes and anodes simultaneously. That means each subchemistry of sodium-ion will develop more slowly, which makes it more difficult to build economies of scale to compete with LFP batteries. Fourth, the sodium-ion industry needs to develop maturity. That is, it needs to get organized to focus its energy on key challenges. For example, effort needs to be put into stabilizing and localizing the sodium-ion battery material supply chain. There needs to be technical standardization for cathode and anode production routes, and key markets like energy storage and low-speed electric vehicles need to be prioritized to increase the odds of breakthroughs. Fifth, battery scientists and engineers on the customer end will be hesitant to take on the technological risks of using a new battery chemistry. For example, a comparative study by the Qingdao Institute of the Chinese Academy of Sciences found that certain sodium-ion battery chemistries experience thermal runaway at an earlier temperature than LFP batteries due to the presence of sodium clusters in hard carbon. That is, they found that deposits of pure sodium metal can form in the voids of the hard carbon, which are reactive and can make thermal runaway more likely than with LFP batteries. It's those types of unexpected challenges that engineers would rather just avoid by sticking with mature chemistries like LFP. In summary, some people viewed my last video on sodium-ion as overly bearish because it didn't align with the bullish narratives in the battery sphere. I can understand why that is. Batteries appear to be just simple cans, so it's easy to dismiss the excruciating engineering challenges of bringing a new battery chemistry to market. While it is true that the sodium-ion battery industry can ride the coattails of the lithium-ion battery industry to accelerate its growth, it's also true that every battery chemistry is like an alien life form with a unique biology rooted in physics. Those physics-based differences mean that the drawbacks of each chemistry can never be fully addressed. Instead, engineers and scientists do what they can to incrementally improve the chemistry, which can involve the entire supply chain, from raw materials to finished battery cell. That, in turn, means each chemistry has its own multi-decade optimization journey. That's likely part of the reason why it took CATL about 5 years to form a supply chain to ramp sodium-ion batteries in earnest. Now that's in place, mass production starts this year in China, and they're launching the world's first mass-produced sodium-ion passenger vehicle. But, as the research paper that I covered today showed, that doesn't mean sodium-ion can ramp at will, or that there's enough demand for those cells. Before I close out this video, although there are a lot of creators out there covering sodium-ion batteries, there are two in particular that have made videos that I've gotten a lot of questions about because our audiences overlap. First, Ryan of Ziroth did a video where he stated that one patent application in particular for antimony-coated sodium-ion cathode material will make CATL's batteries insanely cheap. It's an interesting video, and I'll link it in the description. It is true that antimony-coated sodium-ion cathode material would increase the likelihood of using an aqueous coating process instead of toxic NMP, which would reduce costs. However, as I showed in this video, the challenges that sodium-ion batteries face are broad-based and involve the entire supply chain, So, although an antimony cathode coating is potentially very useful for lowering costs, it's one of many innovations that'll be required to make sodium-ion batteries insanely cheap. So, what's the biggest potential industry-wide catalyst for sodium-ion batteries to drive their cost below lithium-ion batteries? It's less sexy, but high lithium prices, which would create a forcing function for broader-based adoption by customers and companies. That, in turn, would drive growth and therefore innovation throughout the entire sodium-ion supply chain by way of Wright's law, which would accelerate the cost curve by many years. As a side note, it's also worth noting that the gravimetric energy density of sodium-ion batteries is overemphasized as a driver for their adoption. That's because despite their now reasonable gravimetric energy density, their volumetric energy density is still poor. That's one of the reasons why CATL's new Skyline sodium-ion battery pack has an energy capacity of about 45 kilowatt-hours, as compared to over 100 kilowatt-hours for an LFP alternative. That will improve over time, but in the very best case scenario, sodium-ion will only ever be able to achieve about 2/3 of the volumetric energy density and therefore battery pack capacity of LFP. If you'd like to know more, I covered the reasons for that in my last video on sodium-ion. Either way, the lower energy density of sodium-ion batteries compared to LFP batteries means there needs to be some other driver for the adoption of the chemistry, especially in the current market, where sodium-ion batteries don't yet offer a cost advantage on a per kilowatt-hour basis. That driver will be their combination of durability, charging speed, and wide temperature operating range, where sodium-ion batteries dominate lithium-ion batteries. That is, increased adoption is about playing to the strengths of the chemistry, which is why CATL is advertising sodium-ion batteries for products like grid storage and sprinter vans. Delivery companies, for example, will happily take a sprinter van with a battery pack that's half the size of an LFP battery pack, but that's cheaper, offers faster charging, and doesn't need extra time or energy to preheat in cold weather. Lastly, it's worth noting that when I analyze battery chemistries, I'm mainly looking at them from the lens of someone who's invested in EVs and grid storage. But there are, of course, other markets that I know my audience is curious about. For example, the consumer market for home battery storage. Will Prowse is doing an excellent job covering sodium-ion batteries for home battery storage, and he's found that they still have issues with capacity and performance, high cost, low efficiency, and the need for thicker wire because sodium-ion batteries reach lower voltages, and therefore run at higher currents than LFP batteries. That is, for home battery storage, it's still a no-brainer to pick LFP batteries. If you'd like to know more, I'll link some of Will's videos in the description. As always, please consider supporting the channel with the links in the description, which now also includes a referral link for Signature Solar. If you use that link to purchase home battery or solar equipment, it nets me a small percent-based credit. But that can add up on a large purchase, and it really helps the channel. On that note, a special thanks to my YouTube members, ex-subscribers, and all the other patrons listed in the credits. I appreciate all of your support, and thanks for tuning in.